is my first time in India. It's very exciting for me. Thank you. Time travel. It sounds like something ripped out of the pages of science fiction. Is it really possible for us to travel through time? Who of us have not wondered what's going to happen next? What's in our future? And who of us has not wondered about the past and said, what if I could go back in time and change something in the past? Is this possible? Is it just a fantasy? Well, it's more than a fantasy. It's a reality. It's a reality based in solid physics. And the physics that I'm talking about is the physics associated with this person behind me, who I'm sure all of you recognize. This was considered by Time magazine to be the person of the last century, Albert Einstein. However, this is not the Einstein that actually developed the revolutionary theories of relativity that I'm going to be talking about. If I can get this to operate properly. Okay. I think maybe the battery is out of this. Okay, fine. Okay, yes. All right. That's fine. Okay, the Einstein that developed the theory, yes, please, is this, the young Einstein. Einstein was 26 when he developed this theory of special theory of relativity. This was taken in 1905, and I think, hopefully, my laser pointer will work. Yeah. Yes. Is that what the remote? This one? Oh, how do I change the slides? Oh no, I have both. I just wanted to know change the slides. Okay. That's all right. Okay. What did Einstein do? How did he show us that time can be altered? What he did had to do with some simple physics, the physics of motion. What do I mean by that? Well, suppose that I take this ball and I toss it at you. I don't do that anymore. That ball's going to be coming at a certain speed depending on whether I'm standing here and tossing the ball at you, or suppose that I'm running towards you and toss the ball. You know that the ball's going to be coming at you a lot faster if I'm running towards you than if I'm standing still, right? And that's just simple physics. Next one. Okay? So, if I, in fact, toss an object at a certain speed, and I have to get my self coordinated here. I think sure. All right. If I'm standing out here and I have a friend that's tossing a ball at me, suppose that the vehicle is moving at 50 miles per hour. If they're tossing a ball at me, and the vehicle is moving at 50 miles an hour and you're tossing the ball at 10 miles an hour, and if I'm standing out here, you know that I'll just simply see the ball coming at me at the speed of the ball plus the speed of the vehicle. In other words, it's going to be coming at me at 60 miles per hour. If it's tossed in the other direction, then relative to the vehicle, relative to the ground, this is going to be moving at 40 miles per hour. Now, this is just simple physics. Let's suppose, however, that I look at something else. Suppose if I look at light. Suppose if I look at light. Suppose that I shine this light beam at you. What Einstein developed was not only a theory of relativity, but he also made a contribution to another major field, quantum physics. As you may know, what Einstein said was that even though this light beam seems as though it's continuous when I'm shining it at you, that's not so. It's not continuous. Light is made of discrete little balls of light, particles of light, that are called photons. And these photons are traveling at 186,000 miles per second. Okay? So it's because of the fact that there are a huge number of them that it looks like this is a continuous beam coming at you. So if you think of light as being a ball of light that's traveling towards you, then when I'm standing here shining the light at you, it's coming at you, those balls of light are coming at you at 186,000 miles per second. If I'm running towards you with this flashlight, then those balls of light, just like the ball here, should be coming at you faster because I'm running towards you, right? Wrong. In fact, that's what all the physicists of the 19th century thought. They thought that light, a ball of light, would act just like an ordinary ball. That is to say, that if a ball of light is coming at you from a stationary source, it'll be coming at you at one speed, 186,000 miles per second. But if the source is moving towards you, then the ball is going to be obviously coming towards you faster, the ball of light. What they found out, however, was the next slide. No matter, in fact, the real experiment was done with the Earth. It was done in 1887 by two physicists, Michelson and Morley. What they did was they used the Earth as the vehicle. This is a sort of a cartoon version of that. But what they found was that no matter what, if you were standing here and the vehicle was moving towards you, what you found was that the speed of light was not coming at you at 186,000 miles plus 50 miles per hour. The speed of light was coming to you at just 186,000 miles per second. And if it was going in the opposite direction, it was still coming at you at 186,000. In other words, the speed of light wasn't changed no matter how fast the vehicle was moving. Now think about what that means. Think how strange that is. That would be as though I was telling you that this ball was coming at you no matter how fast I was moving towards you. In other words, that would be like me telling you that this ball was coming at you the same speed now as if I'm running towards you. How can that be? How can it be that light is not being changed by speed? Einstein said, and in fact, he was the first one to say, that's because the only reason that light, and the only way that light can stay the same, no matter how fast the source is moving towards you or away from you, something else has to change. And Einstein said that something else is time. The only way the speed of light can stay the same is that time has to change. Einstein said that time changes for the moving vehicle. In other words, the faster the vehicle is moving, the more time slows down, and that's what allows the speed of light to stay the same. Okay? So once again, light does not change no matter how fast the source of light is moving. And the only way that can happen is time has to change. Now you might say, well, has this been shown? Has it been shown that time can actually be altered by motion? As a matter of fact, it has, by a number of different experiments. One dramatic experiment was done at the Naval Observatory in 1971. This experiment is little well not known by the public generally, but it involved using 2 atomic clocks. As you know, an atomic clock is the most precise timekeeping mechanism we have. What the scientists did was to take one atomic clock and keep it at rest at the Naval Observatory. The other atomic clock they put on an ordinary passenger jet, and they flew it around the world at the speed of sound. When they brought the passenger jet back and compared the 2 clocks, they found that the clock on the passenger jet had slowed down. It had lost time compared to the clock that had been at rest. That shows that what Einstein predicted is real. Remember that the scientists, your heart rate, your metabolism are clocks. This means that their heart rate slowed down. This means that they aged less than their counterparts who weren't moving. Now you might say, how come this wasn't news known all the way around the world? The reason why was because of the fact that the speed that affected the motion, the time effect, was only by fractions of a second. In fact, by nanoseconds. Okay? Now, remember that according to Einstein, the faster the vehicle moves, the more time will slow down. You might say, well, wait a minute, the speed of this plane was going at the speed of sound. Okay, so, and that's about, what, 720 miles an hour? That's fast. However, compared to the speed of light, that's slow. Let me give you an example. Light is measured in terms of what are known as Mach numbers, as you know. 1 times the speed of sound is Mach 1. Okay? And we passenger jets can do Mach 1. Ordinary fighter jets can do Mach 2. And we even have stealth fighters that can do Mach 3. 3 times the speed of light. Sound. Now, Mach 3. Let's suppose that we translate the speed of light into Mach numbers. It turns out that the speed of light is traveling at Mach 1,000,000. In other words, compared to the speed of light, the speed of sound is standing still. According to Einstein, the faster we move, and eventually NASA, in fact, you will have a speaker who will be talking with you tomorrow from NASA, who will be talking about advanced propulsion systems. And NASA, in fact, is working on advanced propulsion systems that it will eventually, theoretically, go very fast and maybe eventually approach the speed of light. We never will be able to reach the speed of light. There's a law of physics preventing that. However, eventually we may get near the speed of light. And when that happens, this effect on time will be so dramatic that it will not be in terms of just fractions of a second. It will be in terms of years. We'll see the effect in terms of time slowing down so fast that a person going through time will actually go into the future. And I'll come back to that. Now, there is a dramatic way of seeing this effect of motion on time. There's a device that's called a light clock. A light clock is just 2 mirrors with a pulse of light bouncing between them. One bounce is a tick of the clock. And you can actually see how motion slows down time by using this light clock. Next slide. Okay. And if you could just press on this slide. No. You can go back.
We can see this mysterious effect for ourselves. This device is a light clock. 2 mirrors that face each other with a particle of light or photon bouncing between them. Each bounce